Good evening, Nabila. Am I audible?
Yes, sir. Good evening, sir.
Yeah. Yeah. So let's start. Let's discuss what we were discussing in the last class. Okay. Let's see. So we in the last class, just a quick summary of the last class, we discussed Hess law, right? Hess law
Yes, sir.
indicates that if a chemical change is taking place and if it is carried out in one step or in multiple steps giving the same products, the overall enthalpy change is going to remain same. So irrespective of the path taken, the heat of reaction or the enthalpy change for a reaction is going to remain same. Got it? So and
Yes, sir.
we for that in just one word we told that enthalpy change is state function. State function means uh, it depends upon the reactants and product. It depends upon the initial and final state. It doesn't depend upon the path. Is it clear? So
Okay, sir.
that we have seen in the last class. So Maha, good evening.
Good evening, sir.
Yeah. So Hess law. Just I'm quickly recapping what we discussed in the last class. So suppose there is a reaction in which A is being converted to B and the heat of reaction is delta H1. Is it clear? This is directly being converted. There is one more way to carry out this reaction in which A is converted to X, X is converted to Y, and Y is converted to B. There are certain reactions which can be carried out by one or more than one ways. So what is the value? What is the relationship between delta H2, H1, H3, H4?
They will all be the same.
Yeah, suppose if you are
Even
going
if the
from
difference.
A to B, directly if you are converting, Navila, the enthalpy change is delta H1. This is one of the paths which is leading from directly A to direct B. There is one more path which is going through X and Y. And the total enthalpy change A to X is delta H2, X to Y is delta H3. So total enthalpy change for this path is going to be how much? Or you can write these equations if you are not clear. Maha, you can write the equation that A gives X, X gives Y, Y gives B. Okay. When you add these three equations, this one, and this one, X get cancelled, Y get cancelled, and you have A getting converted to B. Is it clear?
Yeah.
Okay. So, and because you have added the three equations, the heat change will also be added, delta H2, delta H3, delta H4. That will be added. So delta H1 will be equal to the sum of delta H2 plus delta H3 plus delta H4. So A to B, the heat change is direct as this, indirect is the sum of these. Because A to B, the final state is from A to B, the overall enthalpy change is going to remain same. Either you commit directly from A to B or indirectly via X and Y. Is it clear?
Yeah.
And the conclusion was that thermochemical equations can be uh, treated like mathematical equation. They can be added, subtracted. Okay. That was Hess law. And with the Hess law, we are able to calculate the heat of a reaction, which we cannot calculate directly. Enthalpy of combustion you are having. Enthalpy of combustion, Maha, what is enthalpy of combustion? Could you please just quickly tell me? What do you mean by enthalpy of combustion?
The change in the heat when 1 mole of any substance is being uh, compressed or
Completely,
oxidized.
yeah, completely oxidized, burn, right. And the products formed. If I am talking about the standard enthalpy of combustion, standard means you will have, you can see this H naught at the top. Product form will be in their standard conditions. Okay. So whatever the standard conditions are there, for example, water, now 298 Kelvin, it is liquid, so we need to take it as liquid. Is it clear?
Yes, sir.
This is basically enthalpy of combustion. Okay. So this I hope is clear. And so let's
Sir,
see. Yeah.
that we discussed yesterday. So what will be the answer for the second one? Like I could only find like the delta heat, like the enthalpy change for it, but then we have to find the internal energy for it.
Yeah. First, you can write the equation complete. That was for the combustion of.
No, no, in the assignment that we discussed yesterday.
Hmm. So you can write the equation. Whatever the equation is, suppose H2O liquid to H2O. I have checked few more assignments. Okay. And they have there are similar questions given. So whatever the heat which is given in the bomb calorimeter, that is, bomb calorimeter has fixed volume. That is the heat change at constant volume. That is delta
No,
U.
but the bomb calorimeter, that question was like in the other assignment. I'm talking about the assignment that we discussed yesterday about doing it.
Yeah. Okay. So delta H is there or delta U is there. You can write the equation and write the relationship. What was the relationship between delta H and delta U?
Well, I got like delta H as 1.56 kg by per mole.
Mhm.
But then like
Yeah.
to find the internal energy, we need like the T delta T and everything, right?
Got it?
So we just have to substitute the things.
Yeah. You have to put the values of delta NG and RT. Clear? Is it clear? I hope. And with
Yeah.
that, you can, so if any one of the values given, okay, you can correlate them in this way, right?
Yeah. I use that formula, the delta H equals delta U plus PV.
Yeah, PV actually, suppose PV is at constant pressure, what is the volume change? If that is not given, so volume change, you can find it out from the change in number of moles of gases into RT. Because in gaseous state, which you will study later on, PV equal to nRT. This is the equation for gas. P is the pressure, V is the volume, N is the moles, R is a constant, and T is the temperature. So P delta V, if you are want to find out, and if it is not given, we can use change in number of moles of gases into R. Change in number of mole of gaseous substance only because gaseous substance can change in volume drastically. I'm not going to take the change of solid and liquid, that are neglected. Okay, so I
But there
will
was
go.
no change in moles.
Pardon?
There was no change in moles in the question.
Yeah. So then, if there is no change in mole, delta N is zero. But how many gases were there? You need to change in number of moles of the gaseous substance. So delta Ng for this is how much? Is it 0 or 1 or minus 1?
The moles will be one only, right? Because the form is changed.
Yeah, 1 mole of gases on the product side minus 0 moles of gases on the reactant side.
Yeah,
Got it? Is it clear or not? Now,
it's clear.
so with that, you can do delta H equal to, and sometimes there are many questions are given in assignment where they ask actually whether the delta H is larger or delta U is larger. Okay. So, Navila, let's say this is the relationship. So, who is larger in value? Which is the delta
Delta
H
use.
one, delta U is having more value, higher value, because if it is higher, I need to subtract something to make it equal to the lower delta H1. Is it clear? Got it? So this is, I hope the assignment is clear. Let's move to some other types of enthalpies. Okay. Some other types of enthalpies. There are these enthalpy change is the heat change. Okay, that is sure. But depending upon the type of depending upon the name of the reaction, the enthalpy change is also given that particular name as per the reaction. For example, we have seen enthalpy of formation. That was 1 mole of a compound is formed from pure elements under standard condition. That was enthalpy of formation, and that was enthalpy of formation for pure elements is 0. And enthalpy, sum of the enthalpy of formation of products minus sum of the enthalpy of formation of reactants. When it was done on a reaction, you get the enthalpy of the overall reaction. Similarly, we have seen enthalpy of combustion. Okay, so enthalpy of combustion is basically the heat change when 1 mole is completely combusted or burned, okay, into the products in their standard state. Okay, enthalpy of combustion or standard enthalpy of combustion is written like this. Got it? This is standard enthalpy of
Yes, sir.
combustion. There are other enthalpies also. Enthalpy of atomization. What do you mean by atomization?
Enthalpy of
Enthalpy of
atoms.
yeah, changing into
Breaking of
changing
bonds.
yeah, changing the compound
Structure.
in, into completely you are giving it heat so that it changes into atoms. Got it? Is it clear? So let's say, suppose if I take S2 gaseous, got it? And so enthalpy of atomization is basically how much energy I should give to change a given molecule or a substance completely into atoms. Is it clear? So this is enthalpy of atomization. Got it?
Yes.
Suppose if I ask you what do you mean by atomization of methane? So what things you are going to write on the product side?
C plus 4H.
Yeah, carbon, gaseous. So it is the amount of energy which need to be given to one mole of the substance to dissociate completely into atoms in gaseous state. So there are 5 atoms, as you can see, 1 of carbon and 4 of hydrogen. So when you give enthalpy of atomization, all 5 of them break apart. Here,
Yeah.
this is enthalpy of atomization. What do you mean by enthalpy of atomization for sodium? Sodium, what is the state of sodium? In which state sodium is?
Yes.
Sodium is a metal solid. Okay,
Solid.
right? So if I give enthalpy of
Yes.
atomization, it means at 1 mole of sodium solid atoms, they completely get separated from each other into vapor phase or gas phase. This is enthalpy. This is also called enthalpy. It may or may not be equal to enthalpy of sublimation. Okay. This can, here it is equal to the enthalpy of sublimation, but in this you are breaking the bonds also. Is this clear or not?
Yes, sir.
Suppose if you, what do you mean by enthalpy of combustion for chlorine gas?
So Cl.
Yeah. So it is the enthalpy change. Okay. It is the enthalpy change observed when 1 mole of a substance is converted completely into atoms. All atoms are separated in gas phase. Okay. So that's why the name atomization. Got it?
Yeah.
Next is bond enthalpy. Very, very important. Because as the name indicates, it is dealing with the bond energies. So what could be the definition of this bond enthalpy? Or it is,
Enthalpy change when 1 mole of substance bond is changed.
yeah, or it can also be known as, short form is, abbreviated form is BDE. And Nabila, it is bond dissociation enthalpy.
Okay, sir.
So, so energy required to break a bond. Okay. Normally, if you give energy, bond breaking is endothermic. Sometimes this can be equal to the bond dissociation enthalpy. Is it clear?
Yeah.
Right? For this, for this case, so bond breaking is endothermic. It requires energy. Bond formation. Suppose if you take atoms, separated atoms, and they come close and they bind with each other, okay, in gas phase. All should be taken in gas phase. Otherwise, what will happen if you take in liquid? If you are giving the heat, that heat will basically used for evaporation. It will not be bond dissociation. So in this, the energy is released. So I'm telling you the general thing. First of all, bond breaking requires energy if you want to break a bond. And when the bonds are formed, the energy is released. Is it clear?
Yeah.
So suppose if I take methane, it should be in the gaseous form first. Otherwise, it should not be in the solid or liquid form. Right?
Yes, sir.
And suppose if you are giving it some energy and it is completely being separated into individual atoms in gas phase. So this is enthalpy of atomization. For methane, standard enthalpy of atomization to completely convert it into atoms. But there is one more thing which is happening while completely converting it to atoms. Actually, you are breaking the 4 bonds. Is it clear or not? Four carbon hydrogen bonds are being broken, then only this methane will get completely converted to atoms which include one carbon atom and four hydrogen atoms. So this energy is basically equal to 4 times the bond dissociation enthalpy of CH. Is this clear or not? Why 4 times? Why
Yes.
not 3 times? Why not 3 times?
Four
Four
bonds.
hydrogens.
Yeah, because I've broken while changing into atoms, I've broken 4 bonds. 4 CH bonds are being broken. You can see this diagram. So for one, if I give X, another if I give Y, Z, W, whatever the energy. So total for each CH bond, it will be average of all the 4 energies, and that is because we are breaking 4 bonds. So this complete atomization involves breaking of 4 CH bond. So enthalpy of atomization is 4 times the enthalpy of the CH bond dissociation enthalpy of the CH bond. Is that clear? This
Yes.
is basically the mean bond dissociation enthalpy, mean or average. But you need to keep one thing in mind. BDE means bond dissociation enthalpy of CH bond. Is it clear?
Yes.
What will be the enthalpy of atomization? And the bond dissociation enthalpy. Relationship between this for H2O gas.
Would it be like 2H plus O?
Hmm. This is enthalpy of atomization of H2O, standard enthalpy of atomization of H2O. As you can see, the water in gas phase is being completely converted to individual atoms, which include 2 hydrogen atoms and 1 oxygen atom. How this can be related for water? To the bond dissociation enthalpy of the
Also
OH bond.
breaking.
Yes, how many bonds are being broken?
2.
2. So actually this is water. 2 hydrogen atoms are connected to oxygen, so you are going to break the 2 hydrogen bonds. Is it clear? So it is
Yes.
equal to twice the energy of the OH bond. Got it?
Yes, sir.
Is it clear? So this is simple, but you need to take it in the gaseous form. That is very, very important. Why it is needed to be taken in the gaseous form? Why I can not take it in ice form? For bond dissociation enthalpy. So ice, if I give some energy, it will not be used, it will not be consumed to break the bond of the OH. Okay. First of all, the ice will melt.
Maybe because the atoms cannot exist individually when it's in like connected, and only can exist individually when they are in like gaseous state.
Yeah, they can. They need to be taken first. You need to take the reactant in the gaseous state. Actually, first of all, when you are breaking the bonds, when you are measuring the bond dissociation enthalpy, you need to measure the energy which is required to break the bond only. But if you take it in solid, you are not breaking the bond. If you are heating it first, the solid will get converted to liquid, okay, at 0 degree. Ice, if it has 0 degree, so that is, now you need to heat the water. They will give the heat capacity for a specific heat. Specific heat is per unit mass and per degree rise. So if you are taking 10 grams or 18 grams, you will get the heat. You need to convert it into 100 water at 100 degree. Then you need to boil it. Water will change to gaseous form at 100 degree, steam will form. Then you are going to change it into hydrogen atoms and oxygen atoms. Okay. So
Okay, sir.
this is known as enthalpy of fusion. Fusion means melting in chemistry. For 1 mole, it is given. So 1 mole means 18 grams for water. So you start from ice at 0 degree, you get water at 0 degree, but that is being melted now. Ice is being melted. Then this is this doesn't have any name, just an enthalpy change for heating water, because water at 0 degree need to be heated to get it to convert it to water at 100 degree. That will be equal to mass into specific heat of the water. This is not Cp or Cv. Cp and Cv is for the gases. Okay. For this is per unit gram for 1 degree rise in temperature. So for 100 degree, the change in temperature is of 100 degree. You will write 100 degree mass of water, whether it is 1 mole. If it is 1 mole to 18 gram, 2 mole you will write 36 gram, and a specific heat will be given to you. Then this liquid water is converted into steam. This is boiling. Is it clear?
Yes, sir.
So this is actually the enthalpy of vaporization. Is it clear?
Yes. Okay. Yeah.
If I talk about the enthalpy of sublimation of ice, basically it is the direct conversion of solid to gas. Is it clear?
Yeah.
Now in
Yes.
this, so this is called enthalpy of phase transformation.
So, what is S mean over there beside M?
It says
Yeah.
delta T. S is the specific heat of water. Got it? Is it clear or not? Specific heat is for 1 gram. Okay. For 1 degree, how much heat you need? Accordingly, you will multiply by the amount of water and the change in temperature. You will get the total. These enthalpies are known as enthalpies of phase transformation. The first one, the second one. There is one more enthalpy, enthalpy of sublimation. Enthalpy of what do you mean by sublimation? Tell me.
Ice turning it to gas.
The solid changing directly into gas. So heat required to, it is the enthalpy change for sublimation of 1 mole of solid under standard condition. Enthalpy of sublimation means solid to gas directly or vapors. Directly, if something is changed, what is the heat which is needed for 1 mole? That is the enthalpy of the sublimation. Is it clear or not? Got it?
Yes, sir.
So these are called enthalpies of phase transformation. They give you the value of heat absorbed or released when a substance undergoes phase transition. But for bond dissociation enthalpy, you need the reactant in gas phase and the atom should also be in the gas phase because atoms can exist only in the gas phase. If I give the energy to this is not the bond dissociation enthalpy because first the bonds are not going to break. First, the ice is going to melt. If I want the bond energies, I need to take the reactant in gas phase. Okay. This is twice delta bond energy of the CH bond, OH bond. Because there are two OH bonds being broken. Is that clear?
Yes, sir.
Any doubts in this? So bond enthalpy, if there are more than one bond, for example, H2 there are two bonds, in methane there are four bonds. So you take the average bond energies of all the four bonds. But the reactant should be in the gas phase, the atoms formed should be in the gas phase. And bond enthalpies can be used to find out the overall heat of reaction. This is very important. It is equal to sum of the, so you need to count each and every bond. First, you need to count each and every bond in the reactants.
So can you
Because
repeat what the bond enthalpies are used for?
it is bond enthalpy, just like the enthalpies of formation can be used for individual components, can be used to determine the heat of overall reaction. Similarly, bond enthalpies can be used to determine the heat of overall reaction. For enthalpy of formation, if you want to use enthalpy of formation to calculate the overall heat of the reaction, use sum of the enthalpy of formation of products minus enthalpy of formation of reactants. But in case of enthalpy, in case of bond enthalpy, this is reverse. It is the sum. This sigma is represent the sum of the bond enthalpies of the reactants minus sum of the bond enthalpies of the products. Is it clear? This is just the reverse for if you want to calculate the heat of reaction. Standard enthalpy change for a reaction from the heat of formations. So sum of the enthalpies of the formations of products minus sum of the enthalpies of formations. Are you getting a point or not?
Yeah.
Yes, sir.
So for formation products minus reactant for bond energies, you need to break the bond of the reactant first, then only the reaction is going to happen. So you are going to put the reactant and then you are going to put the products. Okay. They also
Yeah.
tell us how strong a bond is. If the bond is stronger, you need more higher. You are going to need higher energy to break it. So let's do one question. Okay, and I hope that will clarify your doubts related to this. Okay. So first of all, in bond enthalpies, you need to, let's say I have given some reactions. I have given a reaction like this. Or let's take one more simpler example. Let's take N2. So how can you express the heat of reaction or the standard enthalpy change for a reaction in terms of the bond energies?
So we'll need the bond enthalpies for it, right?
Yeah. So suppose if I give you the bond enthalpies of bond enthalpy of N triple bond N is 946 kilojoule per mole. Bond enthalpy of hydrogen bond HH bond is 436 kilojoule per mole. Bond enthalpy of the NH bond is 389 kilojoules per mole. Navila, is it clear? These data will be given in the question itself.
Yes, that's clear.
So now you need to tell me what is the numerical value of the heat of this reaction in kilojoule per mole. First of all, are we provided with a heat of formation or a heat of bond energies?
Bond energy.
We are provided with the bond energies, exactly. So we need to use the bond energies formula, and how the bond energies formula can be used to figure out the overall heat of reaction. So we are going to use this formula. So some of the bond enthalpies of the, in this, first you need to break the bond. Okay, so you need to give that much energy. So that's why the reactants are written first before the products. Is it clear or not? So
Yeah.
how much energy do I need to break the into?
It's given, right?
The 946 kilojoule per. Then I need to break the hydrogen also. I am breaking 3 moles of H2. Okay, so plus 3 into, is it clear?
Yeah.
This much energy I need to, because this is for H2 molecule, 1 mole of H2. I have taken 3 moles of H2. Okay. So this much energy is given as positive value, because that is need to be given into the reaction to break them. Then NH bonds are being formed, so heat will be released. So how many NH bonds are formed? As per the given equation.
3. Oh, sorry,
Total,
6.
yeah, total 6. In one ammonia molecule, there are 3. And because in the reaction, it is like this, Nabil, right?
Yes,
So mark,
sir.
totally we are forming 6 bonds. This one, this one, this one, and bond formation releases heat. So we are having 6 kinds of heat is released. Let's take it as 390. It will make the calculation easier. Okay, but this 390, because is the bond being broken or formed? If it is broken, that is positive. If it is formed, it is released. So 6 times. Is it clear?
Yeah.
I
Yes, sir.
need to take the algebraic sum. So whatever bonds are there in the reactant that are being broken, I will count them one by one. The energies will be given. I will take them as positive. On the product side, the bonds are generated and the heat is liberated. I will count the bond individually one by one, and total number of bonds, whatever they are formed, that much heat I will release. Okay, I will put a negative sign on the bonds which are being formed on the product side. Is it clear? So just calculate it quickly and tell me what is going to be the heat of reaction.
Two, three, four, zero.
How much it is coming?
Minus 2340.
Minus 2340 kilojoule per mole. So this is 6 times 390.
Sir, I'm getting 4,594.
The minus 2340 is this one. This one. Of 6 NH bond which are being formed. But I need to take, I broke this N2. I need to add 946. I broke 3 moles of HH bond. 436 into 3.
Sir, shouldn't be like -6?
These are positive.
No,
Because
in
for
the upper,
where?
the above step, like +6 into -390. It should be -6, right? Because of the formula.
Yeah. Enthalpy of formation. Yeah. Correct. Got it. Or I can take it, if I take it -6 here, I will not take it -390. This is one and the same thing. Because these are positive values. Okay, I actually gave the energy minus the bond energy of NH bond 390 into 3. Or I can take -390, or if I take -390, I will take it +6. Is it clear? This is one and the same thing
Yeah.
because this is the heat which is being liberated, heat released.
Because I calculated as like -6 into -390 and got it as like
No, no,
positive 3,000.
no. Actually, I took positive because I took here negative. Or you can take bond energy as the bond always to be positive. Then you can take it this way. So what you can remember, otherwise you will get confused. Okay, bond energies, write them as it is, positive. All the bond energies, if you take positive, so heat of reaction is sum of the bond energies of product minus sum of the bond energies of reactant minus sum of the bond energies of product, where all bond energies are taken as positive. Okay, this formula you can use.
-86.
Yeah. So how much we are getting?
-86 kg per mole.
So let me check it quickly.
94.
This is 2340 946 minus yeah, this is coming out to be -86. Is it clear or not?
Yeah.
Yes, sir.
So basically, take all the bond enthalpies as positive. Remember, you can remember this formula where all the bond energies are taken to be positive. So sum of the bond enthalpies of the reactant minus sum of the bond enthalpies of the product. Got it? Remember this, right? So, and they are in all gases form. So I can directly apply the bond enthalpies. Is it clear?
Yeah.
Or you can take
Yes, sir.
any other molecule, any other reaction in gas phase. So take all the bond enthalpies to be positive. Add all the bond enthalpies of reactant minus sum of the bond enthalpies of product. All bond enthalpies are taken as positive. Just note it down. Okay, then you need not to take that it is formed, so it is going to be exothermic, because this is going to be exothermic, that is already being accounted here. So take all the bond enthalpies to be positive. If you are taking that, then you don't need to consider exothermic or endothermic. Just take the difference. Got it?
Yeah.
I hope it's clear to all of you. Right?
Yes, sir.
Or
So
one
can
more
I do one more
example.
question?
Pardon?
So can I
Yeah,
do
yeah,
one
we
more
can do one
question?
more question. Let's say, suppose we are having a molecule. This reaction you must have studied in class 10th also. This is catalytic hydrogenation reaction of ethene, where the hydrogen is added to the double bond and you get ethane. Bond energy of C double bond C is X. HH is Y. CH is Z. C single bond C is W. To calculate the heat of reaction in terms of X, Y, Z. I hope you understood my question.
Yeah.
I'm not giving the values. I just given you X, Y, Z, W. So you can directly use those. So instead of calculating the numerical value, you can put X, Y, Z. These are taken to be all taken to be positive values.
It X plus Y minus W plus Z.
You need to break a carbon-carbon bond.
Mhm.
So whatever the reactants are there, you break their bonds. So that X amount of heat is given. And there are 4 CH bonds which are broken. 4Z. Is it clear? No, there are 4 CH bonds also, which need to be broken or
Mhm.
separated in the reactor. Then you broke the HS bond. You put in that this much amount of heat. Why? So this is the sum of the bond enthalpies of the reactants. Is it clear?
Yes, sir.
So how are we taking
Yes.
4C?
Yeah. How many bonds are broken on C? This is like this. Carbon is tetravalent, so I need to break 4 bonds. Clear?
Yeah.
So 4 bonds I need to give the, so whatever the bond energy of the CH bond, I need to put 4 times of that energy. So 4 times of Z,
Oh, okay, understood.
right? Then the product, the bonds are formed. So minus sum of the bond enthalpies of the products. So in product, as you can see, there is one carbon-carbon bond being formed, and its energy is W. I will take all the bond enthalpies to be positive. And there are 6 CH bonds. Is it clear?
Yeah.
Yes, sir.
So the answer is going to be x plus y plus 4z minus w minus 6 z. So it is going to be minus 2w minus 2z. Got it?
So in the
Yes, sir.
product sites one, aren't we gonna take add Y also? Because hydrogen bond is also there. Right?
Where in the product side,
Yeah. Like in the reactant side, in the sum we took Y,
in the
but in
reactant
the
side,
what?
you had hydrogen connected to hydrogen. On the product side, you do not have hydrogen.
Oh, okay.
So this is going to be the answer, final answer. They will give you the numerical value, put them, take all the bond enthalpies to be positive. Got it?
Yes,
Is
sir.
it clear? But suppose if the same question is given in terms of enthalpies of formation, standard enthalpy of formation of ethene is P. Standard enthalpy of formation of ethane is Q. What is the standard enthalpy of formation of hydrogen? Is it given to us? If it is not given, what will be the value of standard enthalpy of formation of hydrogen?
Zero.
0. Standard enthalpy of formation of pure elements is taken to be 0. So what is the heat of reaction? Standard enthalpy change for the reaction. In terms of T and Q. For the above reaction.
Minus Q.
Yeah. Standard enthalpy of reaction in terms of enthalpy of formations is enthalpy of formation of product minus enthalpy of formation of reactants. Is it clear?
This is only for
It is,
standard.
yeah, for a standard, or if it is not standard, whatever the enthalpies they are given, if it is at different temperatures, so the formula is going to remain same. sum of the enthalpies of formation of products minus reactants. You need to multiply by the mole of the products also or reactant also, but in this question we have just one mole. So I have not multiplied Q or P with 2 or 3. Okay. Is that clear or no?
Yes.
Right? So in this way we are going to get the enthalpy of reaction. So we are seeing two ways. Either you can take the difference of the bond enthalpies of reactants and products, or you can take the difference of the enthalpies of formation of products and reactants. Okay, so this is the product and this is the reactant. So I hope this is clear to you, right?
Yes, sir.
Got it? Next is, let's talk about some more types of enthalpies. Okay. Lattice enthalpy. This is used for ionic compounds. So lattice enthalpy, when it is given to an ionic compound, the ionic compound in solid state completely dissociate into ions. 1 mole of ionic compound dissociate into ions in gas phase. It is the energy required to break 1 mole of ionic compound into its ions, completely into its ions. For example, if I give, so lattice enthalpy to calcium chloride, its value is going to be different. It is going to be more for calcium chloride because you have more number of ions. So how much are we going to get? What we are going to get?
Ca plus 2Cl.
Calcium ion and this ionic compound dissociate completely into its constituent ions in gas phase. Is it going to be a positive sign or negative sign?
So
Do I
which
need to
one?
give heat? No, both of them. Do I need to give the heat or do the heat will be released?
Heat will be released, right? Because separating the bond.
Heat will be given. Suppose if a wall is there, if the bricks are embedded into each other, if I want to break the wall, what I need to do? I need to put in energy, my energy to break this wall. So this is positive sign. Is it clear? If I want to break the
Yeah.
wall,
Yes.
I need to put in energy, my energy, then only it is going to break. Right? This is going to be positive. But suppose if, let's say, if I take this aluminum ion, and if I take 3 fluoride ion, and I end up with AlF3 solid, so then also the ionic compound is formed. It is not broken into ions. The ions are combining to form an ionic compound. So the amount of heat will be negative. Is it clear?
Yes,
The
sir.
lattice enthalpy of AlCl. So when the ions come together, their energy decreases and the heat is liberated. Right?
Okay, so basically the combination reactions are all negative and then the decomposition reactions are positive.
Yeah, exactly. Yeah, decomposition. So with this, you can find the enthalpy of formation of an ionic compound. You start with the normal elements and you convert them. Enthalpy of formation, the idea, that definition we have already discussed in last but one class, right? So there we had seen that the enthalpy of formation is actually the sum of the enthalpies of formation of product minus sum of the enthalpies of formation of reactants. But in this case, I cannot do this because these are zero. So I need to adopt a different route, which is in line with the Hess law, which says that the reaction can be carried out by different means, but its overall enthalpy is going to remain same. So what I did is, this is the enthalpy of formation if I directly get them, and if I indirectly get them, I will first started with sodium solid and converted into sodium gas. This is enthalpy of sublimation of sodium. Is it clear? Then you are breaking a bond, so positive, but you are breaking half mole of bond. So bond dissociation enthalpy is for 1 mole of bond. This is half mole, because the balance equation is such that you require only 1 Cl, so half mole of. Got it?
Yeah.
Now convert this sodium to sodium plus. This is known as enthalpy of ionization. and Cl2 Cl minus, because we need to prepare them so that they can combine together to form NaCl. So Na is in NaCl, Na is in plus, and Cl was in minus. So we need to convert them, and Na gases or Cl gases, atom gases, need to be converted into Na plus and Cl minus. So Na plus one electron need to be removed. So to ionize, whatever the enthalpy change is there in the gas phase, that is called enthalpy of ionization. Enthalpy of ionization is the enthalpy required to ionize 1 mole of gaseous atom into 1 mole of ions in gaseous state. Similarly, this is enthalpy of is known as electron gain enthalpy. All these data will be given to you numerical values. They will be provided to you, so no need to worry about that. And now Na plus and Cl minus, they will combine together. The lattice energy will be required or it will be released. Will it be required or will it be released?
But it will be
It
positive.
is, what is the sign here? Am I breaking something or something is forming? It is being formed. Right, Nabila?
Decomposition reaction is happening, right? So positive.
It is decomposition from here to here.
From NaCl to Na plus Cl.
Na plus and Cl minus to NaCl. Is it decomposition or the formation? They are coming together or they are
Combination.
going on? It is a combination. Combination means it is released. Okay. So
negative.
minus yeah, negative of okay.
Yes, sir.
Here.
Yes.
So now this was the overall ether formation. But I was not able to get the idea of overall ether formation. So I took a different route. And Hess law says so enthalpy change for a reaction will have a fixed value irrespective of the path adopted for the change. I'm going to sum them up. Got it?
Yes, sir.
So this complete path for the formation. So you will be given these values, you can put these values and you will get the overall heat of formation. This is known as Born-Haber cycle. It is basically same as that of Hess law only. Got it?
Yes.
Same as Hess law. You will be put these values and you will get the value for enthalpy of formation of NAC. Right?
Right.
Next is, yeah. Is it clear? Everything in this?
So like we did in the cycle over there in the upper part, will that be given or do we have to do it ourselves?
Actually, what they do, they give rest all the data except one, and they ask you what is that value. So if they
So
give
they will
this
give
value,
this whole thing.
yeah, they will give you all the things except one value. So if they give this value, this value, this value, they may ask you this. They will give rest of it. So you need to equate the direct with the sum of the indirect values. One of them will
So
be missing.
the total heat will be given.
The total heat will be given, or sometimes they don't give it. They give these values, all these values, and they ask you what is the total heat. That also they can do. So any one of them will be missing. Rest all will be given. So you are going to write the relationship. So one of them will be missing, and all rest of the delta H value will be given to you. You can calculate. Got it?
Yes,
Is
sir.
it clear or not? So now is Yama. Is it clear?
Yeah.
Next is enthalpy of solution. So when enthalpy of solution, as the name is indicated, when you take 1 mole of any substance, when 1 mole of a substance is dissolved completely into the solution. So enthalpy change when 1 mole of a given substance is dissolved So to form a solution of its ions or of the compound. If the solution is water, then it is known as enthalpy of hydration. If the solvent is water, enthalpy of solution is equal to enthalpy of hydration. Okay. So let's take a very common example. Suppose if you take 1 mole of salt, common salt, okay, that is NaCl, and you mix it in excess of water. So whatever the enthalpy change, because if it is water, I can use the term hydration. So this also can be broken into steps and calculated. So NaCl, first you can give some lattice enthalpy, right?
Yeah.
So that will break it into Na plus and Cl minus. Then you can put them in the water. So when you put them in the water, the NaCl is Na plus is surrounded by the water molecules. Cl minus also gets surrounded by the water molecule. So it is basically the enthalpy of hydration of Na plus and enthalpy of hydration of Cl minus. So this is overall enthalpy of solution. You can write it enthalpy of hydration, or you can write it as solution. Okay, general I am expressing. Delta is solution. Because think that you are mixing NaCl. So basically you are doing two things. First you are breaking Na and Cl. So for that you require lattice enthalpy. Then the Na plus and Cl minus, once they are broken or separated, you are putting them in water. So they are surrounded by water, and that is called hydration enthalpy. So enthalpy of solution of NaCl is sum of the lattice enthalpies of NaCl and the hydration enthalpy of Na plus ion and the hydration enthalpy of Cl minus. Is it clear?
Yes, sir.
So
Yeah.
we will revise it in the next